Hello, this is Jennifer Martinez. In this video, we're going to look at related rates. We're going to look at problems where there are at least two changing variables and see how they're related. Let's start by looking at our first example. A spherical snowball is melting. Its radius decreases at a constant rate of 2 centimeters per minute from an initial value of 70 centimeters. How fast is the volume decreasing half an hour later? So when it asks how fast the volume is decreasing, how fast means with respect to time. But if we look at the formula for volume and we try to take the derivative of this, we can see that this would be with respect to r, not with respect to time. So there's an issue. The other thing here is you might think r is a constant, but actually it is changing because here's a spherical ball and here's the radius r, and it is melting. So this r is actually some function in time where it's actually changing. In this particular problem, we can find the formula for r, but you can see in the next one we cannot, because we know r, it says, is decreasing at a constant rate at 2 centimeters per minute. So we know, I'm just going to write that, dr dt is equal to negative 2 centimeters per minute. We have that we'll use later. And it says it starts from initial value of 70. And since it says constant, and it doesn't need to be constant with these problems, but this one, the first one, it is, I can say that we can write a line for this. And we know the equation for the line is mx plus b, or start with the initial 70, I could say that. And then this one with respect to time, because this is per minute. Or this could be the slope, and this could be the initial amount. So you could write it as negative 2t plus 70 if you'd want to use your mx plus b formula. So notice what we have here. We have here dv dr, which by the way is 4/3 times 3 pi is a constant, r squared. Okay, which is, by the way, the same as the 3's cancel, 4 pi r squared. And we have dr dt, we said over here, is negative 2, and it's in centimeters per minute. We're looking for dv dt. So you can see that dv dt is really, by the chain rule, dv dr times dr dt. So we get 4 pi r squared times that negative 2. That is how dv dt is related to r. Now they're asking us how fast is this 30 minutes later. And again, you can't plug in 30 minutes here, but luckily for us, you can figure out what the r is when t equals 30. And we are in minutes here, because we know that r is equal to 70 minus 2t. We have not used that yet. So if you plug that in, you can get 70 minus 60, which is 10. And that would be centimeters. So you can see here that this would be 4 pi times 10 squared times negative 2, or negative 800 pi. The units is going to work out to be, if you think about this was in centimeters cubed, right? So this one would be actually centimeters cubed divided by centimeters. It would be a centimeter squared, wouldn't it? Which makes sense, because if you plug in an r here, that would be a centimeter squared. And then, So this would be a centimeter squared. And then this -2, that was in centimeters per minute. So we're going to get here centimeters cubed per minute, which is exactly the rate of change. The volume divided by minutes would be the rate of change of the volume. We did it. How fast the volume is decreasing a half hour later. For this problem, you actually wouldn't need to use the chain rule, but most of the time they do not give you this other formula, because you could have done this by, let's call this method 2. We could have done this by plugging in the r right into that formula, because that's r cubed, which is 70 minus 2t cubed. And then we wouldn't have that extra variable to deal with. We could have just taken the derivative with respect to time and would have gotten 4/3 pi times 3, 70 minus 2t squared times the derivative of the inside, which is that -2, and plugged in a half hour later, which is 30 minutes, and you would have gotten the same answer. The 3's would cancel. You plug this in here, you would get 70 minus 60, or 10 squared times -2, which is still that -800 pi. And you can clearly see this would be centimeters cubed per minute. This was a good problem to start because there was those two methods, but usually problems do not have that second piece of information. So let's do this example where it does not. A spherical snowball melts in such a way that the instant at which its radius is at 20 centimeters, its radius is decreasing at decreasing at 3 centimeters per minute, which it is negative because it's decreasing. At what rate is the volume of the snowball changing at that instant? This is a more realistic scenario because we don't know how that radius is decreasing. It could be decreasing not at a constant rate. It could be decreasing at a variable rate. But we still can find that instantaneous rate of change. We still have the same picture. It's actually 3D, but this is the two-dimensional picture of it, and there's the R. We still have the same formula. Volume of a snowball would be 4/3 pi r cubed. We do know that right at r equals 20 centimeters, we know that the radius is decreasing at -3 centimeters per minute. We just don't have that formula, which is okay, because we can still find dv dt. Do method 1, which we know is 4 pi r squared. It's not the same variable here, and r is changing with respect to time, so it's not constant. So we know we need to multiply this by dr dt using the chain rule. And if you notice, you can plug all this in. So at r is equal to 20 centimeters, we know that dr dt is also -3, and hence you have the answer. 400 times 4 times -3 would be -4,800. Still have that pi, and we'd still have centimeters cubed per minute. Does make sense because this is a squared times a centimeters per minute, which would be centimeters cubed per minute. Or if you wanted to figure out the answer without involving pi, you can multiply pi, 3.14, about, times that -4,800, and you would get about -15,080 centimeters per minute. What does this mean? It means that the volume is decreasing at this rate, at 15,000 centimeters per minute, about, at the moment that the radius is 20 centimeters. At that moment, that is how fast the volume is changing with respect to time. How fast usually means how that is changing with respect to time. And notice that we were able to find that without actually knowing the formula for what R was with respect to T. Okay, hope that helps.